Okay, let's look a bit more about this expanding the binomials. So 1 plus x to the power of n obviously is 1 plus x times 1 plus x times 1 plus x, and we've got n of them. Now, when we're actually expanding parentheses, what we're doing is we choose one term from each of the parentheses and multiply them together. And then to get the full expansion, we make sure we've got every combination that we possibly can. So using that idea, I can say, well, hang on, if I wanted to work out how to get something x cubed, well, I could have in the first parentheses chosen the x, then in the second one choose the 1, and then in the next one x, then the next one 1, and the next one 1, and the next one 1, and all the rest being 1 up until I get to the last one x, and that would get x cubed. But that of course is only one way of doing that. So the question is, how many different ways? Well, what we're really saying then is, how many ways can I choose 3 x's from these sets of parentheses? And there's n sets of them. So from the n, I want to choose 3. NC3. So the binomial coefficients, yes, whilst Pascal's triangle was a lovely way of doing it, once you start getting past the first few rows, if you haven't already drawn it up, okay, you've got to draw up the whole thing to work out what the coefficients are, but in reality they're the same as our combinations. So our general expansion of a binomial, we could say, is, well, NCK will always be the coefficient of x to the power of k in the expansion 1 plus x to the power of k. Alternative notation for NCK is, it's not a fraction, so notice there's no fraction bar there, it's just n k in two sets of, well, not two sets of parentheses, but in two parentheses. So the actual expansion would be NC0, NC1x plus NC2x squared, plus so on and so on and so on up to the last one, NCN x to the power of n. Now, that's if it's 1 and x, but obviously we could have any terms there. So if it was a and b, again, the binomial coefficients are just going NC0, NC1, NC2, up until the last bit. But again, the powers of a will start at n, and they go down by 1. The powers of b go up by 1. At any point in time, if we add the two powers together, we should get n. So there's my example, 2 plus 3x to the power of 4, which, okay, yes, we could do by expanding the whole thing out. But now I can say, oh, well, hang on, that will be 4c1 2 to the power of 4. Sorry, 4c0 2 to the power of 4. 4c1 2 cubed 3x. 4c2 2 squared 3x squared. 4c3 2 3x cubed. 4c4 3x to the power of 4. And all of that turns out to be this lovely expression, 16 plus 96x, 216x squared, 216x cubed, and 81 to the power of 4. So I don't actually have to draw up Pascal's triangle to do it. Now, I mentioned yesterday that Pascal gets all the credit for it. I mean, he was not the first person to notice the relationship. I think it goes back to the Chinese, going back to thousands of years ago. Well, they had noticed patterns. They've just, they've uncovered, well, it wouldn't have been books, but whatever they wrote on back then. But they've, found examples of it. The reason I guess it's called Pascal's triangle is more that he came up with relationships between all the coefficients. So a couple of ones that are useful. NCK will always equal this one, n minus 1ck minus 1 plus n minus 1ck. That's basically the creation of the triangle. And what it's saying is, to get any term, so say we're on the nth row, we go to the row above, the n minus 1 row, and we add together the two that are above it. So n minus 1ck minus 1 and n minus 1ck. So that's obviously a handy relationship for creating the triangle. Now I'm going to prove it. Well, 1 plus x to the power of n could be written as 1 plus x times 1 plus x to the power of n minus 1. If I expand out the 1 plus x to the power of n minus 1, so n minus 1c0 plus n minus 1c1x and so on and so on and so on, somewhere in the middle there would be these two terms, n minus 1c k minus 1 x to the k minus 1 and n minus 1c k x to the power of k. If I'm just interested in x to the power of k, well, on the left-hand side, there would just be one term, 1 plus x to the power of n. Somewhere in that expansion would be nck x to the power of k. So the left-hand side, I know it's going to be nck. If I look at the right-hand side, well, the 1 would be multiplied by n minus 1ck x to the power of k, and the x would be multiplied by n minus 1ck minus 1. No, they've got to be equal, because they're both the coefficients of x to the power of k, just two different ways of finding it. So if they're equal, well, we now know nck is in fact equal to n minus 1ck minus 1 plus n minus 1ck. Okay, that's the first relationship. The second relationship, as I've written there, is basically just saying, hey, the triangle's symmetric. Like, if you start at the first one over here, it'll equal the last one over here. If you go in 1 from the left, it'll be the same as 1 from the right. 2 from the left will be the same as 2 from the right, and so on and so on and so on. So nck will always be the same as nc n minus k. Again, the two numbers down the bottom are adding together to give the number on top. So that's talking about the symmetry of the triangle. And the last one is, so we're able to start the triangle. And what that's is really saying is every row starts and begins with 1. So the very first number we put down was 1, and then we could create the triangle from that. So nc0 will equal ncn will always equal 1. And that'll do it for today. So just a handful of questions we'll have a look at.